In this lecture, we're going to continue discussing looping and branching in assembler. In the first lecture, we only really covered the basic if-else statements as well as how we can construct a while loop. So we're going to kind of extend upon that idea and discuss another common loop variant, specifically the do-while loop. And it's actually quite important to kind of recall how a do-while loop works because it has a nice upside that is something we generally don't worry too much about in a high-level language. So let's maybe quickly recap the rough structure of a while loop in assembler. The structure is pretty much we have a label, we could call it whatever, but for clarity, let's call it while. We have another label which we'll call e-while, which indicates the end of the while loop. So you can kind of think of this as the start and the end of the loop body. And we start our while loop with some kind of comparison operation. Okay, so it's your typical while loop structure where you have some kind of binary conditional there. We do the comparison, and based on what happens in this comparison, we use a conditional jump to check if this condition is not satisfied, and if it was not satisfied, we jump to the end of the while and we stop. However, if it is satisfied, we don't actually perform this jump and we continue executing the loop body. And as soon as we get to the end of that loop body, we have a unconditional jump back to the start of the loop, and we repeat in the same procedure again and again. Now in a do while, it's a little bit different because we have, again here I've just indicated something to dictate the start of our loop. I'm just going to call it do while. Again, you could call it whatever you wanted. And the way in which this will execute is we simply execute all the instructions in the loop body, and at the end of the loop we end up performing our Boolean comparison. So this would correspond to the typical do while syntax, where I perform my comparison at the end of the loop body. And based on the result of that comparison, I will decide whether or not I should jump back to the start of the loop. So in this case, if that conditional is true, then I jump back to my do while. If it's not true, I simply terminate. Now, there's a nice upside of a do while as opposed to a while loop, and that is that a do while loop only requires one jump statement, whereas a while loop requires two jump statements. Specifically, it has one conditional and one unconditional jump. Now, this feels like a little bit of a minor distinction. However, if you are executing a loop body many times, say you're, for example, counting up elements or doing some calculation on an array of, say, 10,000, that loop body gets executed a lot of times. And actually, the fewer jumps you have in a loop body, the better your CPU performs. And it does so because of a kind of optimization present in modern CPUs called branch prediction. Now, the idea is that as a CPU is executing instructions, so say these are the instructions it's planning to execute, and let's say it's currently executing this instruction. To save on load times, what actually happens is it will load many of the next instructions into its instruction pipeline, such that when it needs to execute, say, this next instruction, it's ready to go on the CPU. It doesn't need to reload those instructions. So it kind of preloads a lot of instructions. However, if I'm preloading these instructions and I'm over here and I actually decide, wait, I want to jump far down in my code, all these instructions over here will potentially not be loaded in already, which will cause a cache miss, and then I have to kind of empty the instruction pipeline and fill it back up with this extra information. Now, modern CPUs do a thing called branch prediction, where they don't just simply load what is next, they kind of make a best guess as to which branch, if say, for example, you have an if-else statement, is going to be executed. There's a more complicated way in which they make that decision, but basically they have to make a gamble of, do I load path A or path B? So say you can think of this being in a typical if-else statement. Do I load the instructions corresponding to path A or the instructions loading to path B? Now, obviously, if it's a good predictor, it will maybe be right more than it's wrong, but it still has the chance of being wrong, which has a big performance hit. And actually, every time we have a jump statement in our program, we introduce this branching pattern, which makes it harder to optimize. So if we have a loop with as few jumps as possible in the loop body, we actually reduce the number of places where the CPU can make an incorrect prediction, and therefore we can actually maximize performance. A little bit of a subtle concept, but it's actually the upside of using a do while as opposed to a while. Now, the immediate question you'll probably be asking is, okay, that's great. And let's say we're happy with this idea that we want to use the loop structure that has less jump statements. Now, the problem is that a while loop is not exactly equivalent to a do while. I mean, a do while will always execute the contents at least once, where a while loop doesn't. So how do we balance the two? And the way in which this is actually done is we wrap a do while in an if statement. So we do a if, or a simple Boolean comparison, to start with, to basically check if the condition would be satisfied. And then we have our do while inside of this if statement. Now, at first glance, this might feel like we've kind of defeated the purpose, because this if statement would obviously have incurred some jumps. However, we're more focused on how many jumps this loop body has, because this is the aspect of the code that might have to execute thousands or hundreds of thousands of times. So we're trying to get as few jumps in the loop body as possible. So spending the one extra jump for this if statement is trivial compared to halving the number of jumps in this loop body, particularly if we had, say, 10,000 elements to loop over. We now, instead of having 20,000 jumps in that loop body, we only have 10,000. So that's how we actually do this conversion. Now, I bring this concept up because if you write some code in C++ and you use a while loop and you disassemble it, so basically use your compiler to generate the assembler code that it would normally turn into machine code for you. If you look at that disassembled code, you will see that the compiler will convert your while loops to do while loops. That's how prevalent this kind of compromise is, that by default your compilers will actually convert your while loops to do while loops. And they do that for exactly the reason I've discussed, is because it's an easy way to get a nice performance boost. It's obviously something you don't normally think about at a higher level. I mean, it would not make sense to really write your code like you see here, because it's more than likely going to make things less clear. However, when you're trying to maximize performance, it's actually the faster way of doing something. So it's quite interesting in that way. Now, it's important that you can understand that these two end up being equivalent to each other in terms of what they compute, even though the latter will be faster, because many of the examples in the textbook as we go further automatically use this if statement wrapped around a do while loop, as opposed to just using a while statement. So you'll see, or a while loop structure rather. So you'll see that throughout the rest of the textbook, it kind of becomes the normal way in which we do looping, which is not exactly the way in which you're probably most used to doing looping from a high level language. So it's definitely something to make sure you understand, because we'll see the structure come up again and again and again. So let's look at an example, just so we can get a little bit more practice with loops and our assembler. So I'm going to go through this example. This example is in the book, but it doesn't really illustrate what it's trying to do. So I refer to this as ugly C code that will search through a character array. The premise being is that you have some kind of key. So in this case, our key is actually what is stored in X, and you're going to search through this character array to see if that key is present, or that specific character you're looking for is present. If it is, we want to return the index of it. And if we can't find that specific character, we're just going to return a -1. Now, in this example, our character array is your typical char star version of a string instead of a nice high-level language string like in C++ nowadays. But that means we have null terminated strings. So we have a bunch of characters, and then the last character will simply be the null element. So with that in mind, we want to loop through our given character array and figure out if a given specific character, in this case character X, is present in it, and if so, we want to return its location. So this is a bit of C code. It's close on pseudocode because we haven't actually specified the variable types, but regardless, it's pretty much complete. So the first thing we're going to do is I'm just going to use I to be my index variable. So this is the location I'm currently in my character array. I'm then going to set C to be the current character location. You'll notice for simplicity here that we're not doing extra error checking. So I'm not, for example, confirming that I have at least one character in my character array or whatnot. For this purpose, you can assume you have at least one, even if it is in fact the null terminated character. So it's just null. So that would be our empty string in this case. So I load my current character into C, and then I want to do my check to see is C in fact null or not null. Now, obviously, if it's null, it means there's no purpose searching through the string because there's no content, in which case I'll fail to satisfy this into null, and that will mean I'll just jump right until the end of the loop body and then continue executing because there was nothing to look for. Okay, so we couldn't find the element. If, however, we're in a situation where the first character we're looking at is actually not the null terminator, we now need to actually search the content, so we can actually start going through our loop body. So the first thing here is I'm going to check, is my current character equal to the character I'm looking for? If it is, that's great. I'm simply going to break. And now, once I've broken out of this loop body, you'll see that I'll now have to execute this ternary if statement. So in case you're a little bit rusty on your C++, all this is doing is it says if the current character is equal to null, that basically means I got to the end of the string, if that's the situation. If C is equal to the null character, if that is the case, it means I did a whole pass and I didn't find anything, and that means I'm just going to return -1. We're going to use -1 here to indicate could not find the character. If, however, the current character is not actually equal to the null terminator, which would have been the case if we came from this break statement, then my current index I is what I want to set n to, and n is the value I'd be returning. So this I would correspond to the index I'm currently at, and that's the index where I found my character that I was looking for, specifically X. Now let's say that I was at this point in the code again, and I didn't actually find the character I was looking at. What would happen? Well, all that happens is I increment I, so I change where I want to look at in the array, my array of characters. I simply set C to be the new element of my character array. Check once again, is it in fact null character or not a null character? If it's not a null character, I simply jump back up to the start of my loop body and I repeat in the same capacity. So simple enough code. It's just a little bit of ugly C because of the way in which it manifests itself in C++ when I deal with null terminated characters. So that's great, and well, we know what we want to achieve with this code, so let's try and rewrite it using assembler. Now I'm going to show you two versions. The one version is more true to the textbook's example, and then I'm going to show you a slight tweak to that answer where we can rely more on 64-bit registers, but I'm going to illustrate where you would need to make the change, because it's not just a simple matter of changing a BL register to an RBX register and assuming everything will be fine. We have to do a couple of extra things like we actually discussed when we first introduced moves, but I think it's worth recapping. Okay, so let's start with our data segment. So for the sake of this example, we assume our data segment is loaded as follows. We have our data, so this will be our string, which is an array of data bytes. In this case, it will obviously be an HE, so on. So this is just hello world followed by a null terminator. Obviously, this could have been input from a user or something like that, but for this example, at least, we have it preloaded into our data segment. I'm going to use n to store the location I find the specific character I'm looking for, and then I'm going to just simply specify the character I'm looking for this example to be W. Obviously, you could read that in from a user and then execute the code or whatever you wanted, but here I'm going to say I'm looking for W specifically. So I've just loaded W into X, and again, this is a data byte because one character is simply 1 byte. So let's start at the beginning. So the first thing is I just want to load the value that I'm looking for into a register because I'm going to be doing a comparison against it frequently. So I want to try and 1, put it in a register so that it's actually quicker to access, and 2, because I obviously don't want to end up in a situation where I have 2 memory accesses in an instruction because that's not allowed. So I'm going to load X into BL. Remember, BL is simply an 8-bit register, or the bottom 8 bits of a 64-bit RBX register. So BL now contains the character we're looking for. I'm going to use RCX to specify my count variable. So I'm just simply setting it to 0. Then I'm going to set AL to be my first element of my array, first element of my character array. And the way in which I do that is simple. I simply say dereference the location data. So remember we have that address plus RCX. Now remember RCX contains the index we're looking at, and because each element of this array is actually only 1 byte in size, we simply just need to use RCX directly. We don't need to multiply it by 8 like we did in the switch example from the previous lecture. We can just use plus RCX. Obviously, for this specific example, you could have actually just used AL and then simply actually had data, because we're really adding 0 in this case. But I think it's good just to put it in here because we're going to use the same structure as we proceed to loop through the array. First thing I'm going to do, and this is basically the if statement outside of my while loop, is I'm going to check if AL is in fact equal to 0. So I'm checking if the current character I'm looking at is null terminated, or sorry, if it's a null entry rather. And if it is a null entry, then we may as well stop the search. And in that case, if they weren't equal, JZ, or jump when the previous comparison resulted in a 0, is not true, I will simply jump to this instruction over here. In which case I will actually just load -1 into RCX, and then I'm going to load from RCX into N. Now remember, N is where I wanted to store the location of what I was looking for. In this case, the way I've run through this example so far, this would be a situation where I failed to find the element because it was just an empty string to start. Okay, but let's say that we didn't actually fail to find, in a situation where we didn't start at least with a null terminated character. We actually want to execute our loop body. So the first thing I'm going to do is I'm going to basically execute this if statement that we had over here. So I'm going to compare AL, which is the current character that I'm looking at, with BL, where BL is the character I'm looking for. If they're in fact equal, I'm going to jump to found. And if that happens, I'll simply move RCX into Rn. Remember now, RCX didn't get changed by this instruction because we jumped over it. RCX will actually simply contain the index we're currently at, so then we'll end up storing the correct index in N. If, however, we're in a situation where my comparison of AL and BL failed, so the current character was not the character I was looking for, I simply continue with the loop body, so I increment RCX, so basically my count variable goes up by 1. I replace AL with the new character I want to look at, so I'm simply going to set AL to be at address data plus RCX, and then I dereference it to get the specific value and store it in AL. And then I do the bottom part of my do while statement. I try and check if I now am at a null character. So I'm going to compare AL with 0. If AL is in fact 0, it means we've hit the end of the string, and in that case, this jump not 0 will not execute, and I'll just continue going down, load -1 into RCX, and that will be what will be set, or that's what N will end up being set to because I didn't find it. However, if I'm not at the end of the string yet, then we're actually going to execute this JNZ, so not 0, such that I jump back up to the start of this do while. Okay, so simple enough. The only thing that's maybe a bit tricky here is that we have a bunch of different variable sizes. Or more specifically, we're using different register sizes. So I have some 8-bit registers like BL and AL, and then I'm using, for example, a 64-bit register for my count. Now, there's nothing wrong with doing this. This is perfectly fine. And actually, this is going to occupy less space in terms of the full set of instructions than what I'm going to show you. But I'm going to show you now just use the 64-bit registers. Okay, so I've indicated with these arrows all of the locations where I change the instruction. And you'll see here that instead of storing X into BL, I know I only want to work with 1 byte, but I want the convenience of always working with 64 bits. So I'm going to load X into RBX. But now, because X is only 1 byte in size, okay, remember all of those characters are just a singular byte, I'm going to have to specify that I only want a byte, and I use 0 extend. So basically RBX will be a bunch of zeros now, with only the last 8 bits containing something from X. Okay, so I basically 0 extend the top part of the array, top part of the register rather, and I just load in the current byte I'm actually looking at. If I, for example, did something like this, where I just went move, and it's a common mistake that I see being made, if I just went move RBX X. Now, what will end up happening here is the assembler won't moan, it will run this command, but you will load, in this case, if in this case it's an 8-byte field, you'll end up loading 8 characters into RBX, which is clearly not what you actually wanted to do. So that's something you need to keep in mind, that doing something like this is always going to load 64 bits, whether that's what you want to or not do. So this is not the correct way of trying to move in X. If you want to just move in 1 byte and you want to move it into a 64-bit or an 8-byte register, you need to use this 0 extend in the case of it being an unsigned number like a character, and you have to specify the size byte. The same thing applies in all of the places where I did a move using just a byte. So here, I wanted to extract a singular byte from my data array, which was my character array in this case. And because I only want to load 1 byte, but into a 64-bit register, I specify a byte and I have to use 0 extend to make sure that the top order bits are 0. This means I'm definitely not loading more data than I intend. I'm only loading the 1 byte, but there's not random garbage on the top end of my array. So I can still work with RBX without having to worry about anything. Or in this case, work with RAX without having to worry about anything. And this is particularly important for this next line here, where I did a comparison of RAX with 0. Now, if I had, for example, done something over here where I went move AL data plus RCX, that's fine in the sense that I've only loaded 1 byte. However, when I do a comparison, if I went RAX 0, this might randomly fail on me because I actually did nothing here to change the higher order bits. So it could be random garbage, and that random garbage is very likely not 0. So I'll never actually be able to satisfy that compare. So that's why you need to make sure that you do the correct load when you're working like this, where I only want to load 1 byte into a 64-bit register. Okay. And you see the last place where the similar change occurred was over here. I basically do the exact same thing. I specify a byte and I specify that I want to 0 extend. And again, I'm doing a comparison against RAX because I'm comfortable working with the whole 64-bit registers now because I know the top order of bits are completely blanked. Now, both ways are perfectly fine, but what I see happen often is that people accidentally use a hybrid of the two. So they decide they want to use 64-bit registers, but they don't actually specify the correct moves or specify the size. Oftentimes, one of those two mistakes are made, or even both. So make sure if you want to use the 64-bit registers, you're aware of exactly what type of move you're actually really using and how much data you're actually about to load. We have another simple looping example. So in essence, in this case, we're pretty much emulating a for loop. So before we emulated a while loop and then a do while loop. So now we're going to emulate a for loop. Obviously, the general structure of a for loop is pretty straightforward to emulate in that it's very similar to how a while loop works. The only difference is your conditional is dependent on some kind of count variable instead of a more generic one. That's it. I mean, you could squeeze a whole array of different type of conditionals inside a for loop, but traditionally at least it's dependent on some kind of counting. So for this example, we're going to assume we have 3 arrays of size n. And for simplicity, we're going to say that each element in this array is a long. So a long is a quad word. So just in case you don't recall, an int in C or C++ on 64-bit Linux would correspond to 32 bits, and a long would correspond to 64 bits. Okay. So if you see an equation where I say you'll get the function, for example, takes in an int, it means that it's taking in a 32-bit value. And if we say that the function is taking in or returning a long, it's referring to a 64-bit value. So for this purpose, we have 3 arrays of longs, each of equal size, specifically of length n. And I basically just want to set the corresponding element of array C to be the sum of A and B. So basically I have A, B, and C. And I simply want, say that's A, B. I want to basically set this element to A plus B, and the same for each of the corresponding elements. So let's try and do this in assembler. Obviously, we can all code stuff like that straightforwardly in C++ and C. Let's do it in assembler. Again, it's not too complicated. There's a couple of nuances that I just want to make sure that we all understand. So the first thing is I'm going to load this in from memory into RDX. So I haven't explicitly shown it here, but let's, in this case, n would have been some data quad. So it could have had some specific value. Let's say it was 15 for argument's sake, but it is a data quad for the purposes of this example. So I move that into RDX, and I'm putting in a register again because I'm going to compare against it frequently, so it's quicker if I can get into a register. I'm going to use RCX as my count register, so I'm going to basically just set RCX to be 0. You'll see here that this is using the fastest way of actually doing that, where I XOR ECX with ECX, which will set the lower 32 bits of the register to 0 and 0 extent above. But I mean, perfectly acceptable would have been to simply say, and as I mentioned before, I would almost recommend you do it this way so that things are as clear as possible for you. Unless, for example, I ask you for an alternative way of doing it or something like that, this is definitely a clearer way. So we set ECX to be our count variable, so it's going to represent our I from our pseudocode from before. And I start and I end my loop using specific labels. Again, I could pick whatever I want, so I've just decided to call the start label 4 and the end of the loop body N4, just so it's easy to refer to. First thing I'm going to do is I'm going to compare RCX. So remember, RCX is my index with RDX. And remember, RDX was just loaded from memory. That's just N, so the size of the array. So I'm doing a comparison between the two. And basically, if I'm in a situation where I is actually not less than N, if that condition is not true, I want to jump to the end. Remember, it's always the inverse of the normal operation we used before. So I'm going to say, if they've become equal, then I'm going to jump to the end. I mean, you could have technically here also used JGE. That would have worked as well. Greater or equal, that would work perfectly fine as well. So here, if this conditional is not satisfied, I jump to the end of the loop body and I don't have to worry. But let's say we have not gotten to the point where I is larger or equal to N, and it's still less than N, and we want to do the internal body of the loop. So I want to basically do this line. How do we go about it? So first thing is I'm going to load the value AI, so the ith element of array A. And how do I go about doing that? Well, I'm moving it into a 64-bit register. A will point to the specific location in memory of this array. And then I want to go to index I. Now remember, RCX contains our index I. So I use plus RCX. However, because I said this is an array of data quads, it implies each element of that array is actually 8 bytes in size. So I can't just say A plus RCX because that would only move me 1 byte. I actually want to move 8 bytes for each increment in RCX. So I simply say A plus RCX times 8. Okay, so this will basically move me to the next element of my array. So I was maybe, for example, at this location here, reading this data, and when I add RCX times 8, I move to the next location. So say RCX was 1, it would go to this location in the array. Again, if I didn't have this times 8, I would end up having moved some kind of midpoint here where I'm still technically in the first element. So how much you move is dependent on the size of the element. So in this case, it's 8. We'll see later on when we start building structs, and I might have an array of structs, how much you actually need to multiply these numbers by will actually depend on the size of the struct. It gets more complicated then. But for the moment, times 8 works fine for us. Then I'm going to simply add to RAX. So RAX, remember, was just AI. I'm going to add BI, accessed in the exact same way as I did for AI. And now that they're added together, I simply want to store them into my corresponding element of array C, so into CI. And you'll see I just perform a move from RAX back into that specific element of the array. Now note here that you may have been tempted to try and merge those two. However, if you, for example, try to perform a move or an add and you had 2 memory accesses, the command will not work. Remember, this is a reminder, in assembly, you cannot have 2 memory references in a single instruction. You can have at most 1 memory reference in an instruction. So once we've done our calculation and gotten CI and stored it, I'm simply going to increment RCX, my count variable, and then I'm going to jump back up to the start of the loop, and I repeat the process again and again. So nothing too complicated here, it's just getting getting more comfortable with the notation. The big trick with these kind of loops in general, or just getting looping right in assembly, is to try and be very careful of how you think about using these conditional jumps, because it's very much inverted logic. So you could have also, instead of saying, you see that JE or JGE would have worked in this case, but actually J not less would have also worked out perfectly fine. So you have a couple of options in reality for this example, at least. Most of the time you're a bit more restricted, but it's very important to understand why you're using a specific conditional, and that what's interesting is you jump in the situation where the conditional is not true, which is very different than the way in which we normally conceptualize conditionals in a high level language. So let's try and actually do a nested loop. So the previous examples have only been one layer deep, but obviously we can have nesting as deep as we want in assembler. And in most high level languages, that's the case. Some languages have a nesting cap, but most of them, for all practical purposes, are basically non-finite. So we want to calculate this double summation. So I want to sum from j equal to 1 up to j equal to I, and then I want to repeat that process from I equal to 1 all the way up to I equal n. So all this basically means is that I have 1, and then I'm going to add to it 1 plus 2, and then I'm going to add to this 1 plus 2 plus 3, then I'm going to add to this 1 plus 2 plus 3 plus 4, all the way up until n. Okay, so it becomes a very large sum quite quickly. So how do we go about doing that? Well, if you're kind of up to date with your combinatorics, you can actually mathematically deduce what that summation is. For a given n, you can actually get the answer in constant time. But for the purposes of this demonstration, let's assume our combinatorics are not that up to date and we don't know how to do it straight away, and we want to just do this via a nested loop. So it's a nice simple example to demonstrate how we can nest loops. So first things first, let's just define some of our data segment. I'm going to use a variable sum, which is going to be a data quad, and that's where I'm going to store the result of my calculation. So in essence, sum is going to be equal to that double summation. And then I'm going to have another variable here, n, and this n is just going to correspond to the n that I use in the double summation. Obviously, this is just for demonstration, but I mean, you could get a user to input a number. You convert it from an ASCII character to an actual number, and then you could store it in n and then perform the same kind of calculation. So this is our little loop body. You'll see again, as I mentioned, you can specify the labels of whatever you want. What I've done here is I have loop 1 and loop 1 just as a shorthand for myself. This is the start of the loop, end of the loop, and I've indicated loop 1 because this is going to be my outermost loop. Then I have another two sets of labels here where I have this loop 2 and loop 2. This is to indicate the internal loop, so the nested loop. Now, there's two things. As I mentioned, you could pick any names. I could call this A, B, C, and D if I wanted to, and that would be perfectly fine. It's not very understandable, but the program would work perfectly fine. The other thing here is this indentation that I've done, specifically that you see that I'm at a different level of indentation, depending on which loop I'm actually working with. That is not something that assembler imposes. That's just a kind of a common coding standard in assembler programming, that you utilize the indentation to make it clearer for the nesting. But it's not a language construct. It's very much something that we kind of have decided is a good syntactical idea to make things clearer. But it's not something imposed upon you by the assembler. Okay, so with that out of the way, let's run through this little double loop. So first thing is I'm going to extract n and move into RBX. So this is our outer count. So with that example, n was 5, but this could be any number. And then I'm going to use RAX as my normal accumulation register. So I'm going to basically use RAX for my sum. Then I'm going to use R8 as my counting register. Now, normally we had used RCX as our counting register, but I'm actually going to use RCX for the innermost loop. So I need to pick another register. So I'm simply going to decide to use R8. Could have been any other register as well already. Could have been R9, R10. It could have been RDX in this case even. But I've decided to set R8 as our, or for at least our representation of I. So I'm going to set R8 equal to 1. And now we start our loops. So the first thing is I'm going to compare R8 with RBX. So basically I'm comparing I with N. If in this situation, I is in fact greater than n, well then I don't need to keep looping. So in that situation, I would jump all the way right up until the end and simply move my accumulator Rx into sum, and I'd basically be done. If, however, I'm in a situation where I is actually less than n, we execute the first loop body. So basically, we're now considering this part here. I'm going to move 1 into RCX, and this corresponds to me just setting j equal to 1. So it's basically this little part over here. I'm setting j equal to 1. And then I'm going to enter my nested loop. So I'm going to compare RCX, so this is basically j, with R8. So I'm doing a comparison of j and I. Now, in this case, I want to keep looping if j is less or equal to I. So that means if j is in fact greater than I want to stop looping and I would simply jump to the end of the loop body. However, if that is not the case and j is in fact less or equal to I, I'm going to actually just execute this inner loop body. I add RCX to RAX. So that just corresponds to this actual addition of this actual term. I add this j to RAX, I increment RCX, and then I jump back up to the start of my loop again. And I repeat this process again and again until eventually I end up in a position where j is in fact greater than I end that inner loop, and I now proceed here that I'm going to increment R8. So this is basically my I for my outer summation. I increment R8, and then I jump all the way back up to loop 1. All the way back up to loop 1. And I repeat this process again and again and again until eventually I've got into a position where I is in fact greater than n, and then I just move whatever I had in my accumulator register RAX into sum. So that's how we were able to actually do nesting of loops. Now obviously you could nest deeper than this. You could have 5, 6 levels. It just becomes harder and harder to track. One thing that would actually happen in reality is you would actually start running out of registers if you nested too deep for count registering. So then you would have to get a little bit more imaginative and store something in memory to save it and then bring it back. But it's an unlikely situation to arise, at least at this point. We'll get into a situation where you have to save register values more carefully when we do actual function calls, when I have to build and destroy stack frames, but we'll get to that next week. So there's another variant of looping, which is very uncommon in modern assembler, but was highly prevalent in old assembler. So the CPU actually has an instruction called a loop, and 2 variants of it. There's actually a couple more, but for our purposes, you don't just have to worry about these 2 variants, which is loop E and loop NE. And they're designed for specifically looping. But how do they actually achieve this looping? Well, the way in which they work, for the moment just consider loop, is that it decrements whatever is in RCX, and then it will branch, so it will basically perform a jump if RCX is not 0. Okay, so it decrements RCX, and if RCX is not 0, it will jump to a specific location you specify. Loop E and loop NE are kind of specializations of that. So it will decrement RCX and it will branch. So in this case, it will jump if RCX is not 0 and the 0 flag has been set in the case of loop E. So you would have some comparison before this. So it's basically you will jump if RCX is not 0 and some condition has been met. And then we have another variant, which is loop NE, which will do the same thing if the RCX is not 0, but the 0 flag has not been set. So it's 2 specialized versions. Now, it's actually in practice a lot faster to just use decrement and jump not 0 to emulate this normal loop behavior. So you manually do what it's doing. And it's not just a little bit faster. I think it's about 3 to 5 times faster depending on the machine to do it manually yourself with this conditional jump and a decrement. But on old architectures, it used to be very fast. However, on modern architectures, it's basically microcoded, meaning that it is implemented using other instructions, and it's actually not fast. So in modern assembler, you won't ever use loop. It's good to understand how it works, obviously, but if you're writing new assembler from scratch for some reason, you should be advised to not use loop because it's actually a slower way of doing looping than actually just manually using compares and conditional jumps. There's actually even a further restriction on using loop, and that's that the label must be between minus 128 to positive 128 bytes of the current instruction in the RIP register. So you can just think of it being a situation that you can't jump very far away from your current instruction if you just use loops. So you can have a very long loop body. You had to have a small loop body to try and use the loop instruction. So there's a further restriction with the loop operation. Now, let's just see how we can use it, so you have an understanding of how it works. But I do stress that if you're writing code from scratch in assembler, I would avoid using loop. Obviously, you should know how it works and you can get questions on it. But if you're writing assembler from scratch for some reason, don't use loop as your first choice, as it's slower to achieve the same thing. And obviously, if you're writing an assembler, your aim is to try and gain some performance benefit. So try and avoid using something that's clearly slower in modern architecture. So let's look at a nice simple example with loop, and you'll see that it is easier to use loop than the conditionals and the jumps, the comparisons and the conditional jumps, but there are those performance hits that I mentioned. So for this example, I want to add 5 to some variable 64 times. So basically I just want 5 plus 5, 64 times. Let's assume we don't know how to multiply for the sake of this example, but let's say I just want to add 5 to some 64 times. So the first thing I'm going to do is I'm going to set sum to be 0. So I'm just going to use RAX as my sum. Could have used something else. I'm going to set RCX to be 64. Then I'm going to specify a specific label. In this case, I'm just going to call it loop 1. Now, in essence, this over here is actually going to act as my loop body. I'm going to add 5 to RAX. And then I'm going to call the instruction loop followed by the label. In this case, the label is going to be loop 1. Now what this will end up doing is it will decrement RCX, and if that decrement did not result in RCX becoming 0, so basically jump not 0, we will go to loop 1. Okay, so basically that's what this loop instruction is doing, is it will decrement RCX, and if we ended up in a situation where the decrement did not result in RCX becoming 0, then we're going to go back to loop 1. So you'll see it's basically this idea of if not 0, we perform this jump. Now, as I said, this is simple enough. However, it is slower than actually just manually using these instructions. Okay, so it's just something to keep in mind. Now, in some situations, you may not need the full power of actually building an actual loop or a more complicated loop structure. Sometimes there are very repetitive, small looping structures in your code. Now, in a high-level language, by and large, you're priced into using a loop structure, even if the contents of the loop are quite simple. However, at an assembly level, we actually have an array of very useful instructions that allow us to perform a loop-like operation without having to go to the lengths of building a full loop structure. And this is referred to as string array instructions, or sometimes simply referred to as string instructions. Now, the name is a little bit, or can be at least a little bit confusing, in that when I say this is an instruction that's meant to work on a string, you might immediately think that I'm talking about a character string. But the reality of it is these are operations that are designed to work on a string of data elements. So this could be a string of bytes, a string of words, a string of quad words. The string is just used to indicate an array in this context. Okay, so don't think of string as a character string in this sense. Think of it as a string of data. So that's the first thing I just want to make clear. So the first type of these operations is the move string byte operation. So the way you can remember the mnemonic is move string byte. So basically the S indicates that this is specifically, or a variant of move that's designed to work with an array, so a string of elements. And specifically the elements are a size 1 byte. Okay. Now this operation actually takes no operands. However, it requires you to front load 2 values into registers, much like it was when we work with, say, for example, division, where we had to load registers before we called the instruction. The same thing applies with move SB, but we also don't provide any operands to it. So the first thing we need to do is we need to load the address of our source data into RSI, and then I need to load the address of my destination data into RDI. Then when I execute move SB, what will happen is it will copy the contents from RSI, so in this case it will be 1 byte worth of content, into the location at RDI, and then it's going to increment both addresses by 1. So if we look at this little example over here, I have two little arrays of bytes. In this case, they happen to actually be characters. And I'm going to call the first one message 1 and the other message 2. I'm going to load the address of message 1 into RSI, load the address of message 2 into RDI. So I'm going to use message 1 as my source data, and message 2 is going to correspond to my destination data. Now the question is, what happens if I call move SB? It's going to take the value from A and copy it into the corresponding location at message 2. So I end up with this string at message 2. And then it's going to increment RSI and RDI by 1 byte. Okay, remember RSI and RDI are stored addresses, so it's going to increment them each by 1 byte. So it would move them up 1 location in that array. So after this instruction, we are basically actually looking at these two elements here. And if I were to, for example, execute move SB again, so say this instruction was over here, what would happen is I would end up setting this 2, so this would end up becoming a B, and then I would actually be at this location over here. And this just repeats for each time I call move SB. Now in isolation, that doesn't seem like it's that useful, because sure, it kind of does a little bit of maintenance for us in that I'm able to make the copy and increment the pointers. So I mean, it does help a bit, but if I were wanting to do this for say 100 elements, I would still have to somehow loop over. So I'd have to, for example, wrap this move SB in a loop-like structure, and there's not that much point at that level. However, there's an instruction at our disposal that we use in conjunction with move SB and the other corresponding string operations that actually makes it work like a loop without having to build a full loop structure. So let's look at that now. So the instruction that we're going to use is called rep, which is short for repeat. And what will happen is if I make an instruction like rep followed by a string instruction, so again, let's just say just move SB, it will repeatedly call the string operation until whatever is in RCX has gone down to 0. Okay, now what it also does for us here is that when I call repeat, it performs the operation and it will decrement RCX. So we might set RCX to be say 100, and then after one execution, it will end up decreasing, or one execution of this move SB, it will decrease RCX by 1, and then it repeats the move SB, and it does this again and again and again, right up until the point that it gets RCX all the way down to 0. Now this is not kind of seen as separate operations. If you were to use this in GDB, you'll see this kind of looks as a single operation, that it does this whole sequence. But it makes our code very nice and succinct instead of having to have a full structure. So let's look at a little example over here. And I'm introducing a new instruction as well, or a new version of move, because the textbook kind of throws them in around this point in the book, so I feel like it's a good time to try and introduce it. But before I actually consider this version of the two instructions, let's just say that I had the instructions move RSI, so basically I'm loading in my source register, so I'm just going to say source, where source would correspond to some array of, in this case, bytes, so some array of bytes. And then I also have my move RDI, and then this would just be some kind of the address of some array in my data segment again. Then what happens is I'm going to set RCX to indicate how many elements I'm working with. So in this case, for example, I'm working with 1,000 elements. And then I call rep move SB. Now what will end up happening is, if if I have my arrays, so let's just call this one source and this one destination, is it's going to copy this value to this location. It's going to increment the source and the destination pointer such that I'm now looking at this element and this element. It's then going to check if RCX is in fact not 0 yet. If it's not 0 yet, it's going to perform the same operation. So it's going to copy this value to the destination, move the pointers, check what RCX is. If RCX is not 0, we're going to end up copying this element into the destination, and we'll repeat this 1,000 times. Okay, so it's a very nice way of providing all of this copying. Okay, now we need to discuss this command that I used here, or this instruction rather that I used, this LEA. Now, LEA stands for load effective address. And as I kind of alluded to, LEA, say RSI, A, so say I have some memory at address A, is equivalent to simply using move RSI A. Now, at first glance, you might decide, okay, well, if this load LEA simply loads the address of A instead of the dereference value, why not just always use the second version? And I'd say for the most part, the second version is perhaps a little bit clearer. However, we get one little bit of extra functionality from using this left-hand version, which you'll see will come up when we start doing more complicated type of array operations, when we do dynamic allocation in particular, is what would I have to do if I didn't want to store A in RSI, but I wanted to install or store A, so the address A plus 8 bytes. Maybe what I wanted was add address A, but it's 8 bytes across. How would I go about doing that? Well, I could go move A into RSI, and then I could just say add, say 8 to RSI. That would work perfectly fine. However, if I use LEA, I have the upside where I can instead simply go LEA, the register I want to store it, A plus 8. And now what this will end up doing is it will store the address of A with 8 bytes added to it. So RSI still contains an address, but it's offset by how much I've specified on the right. You can also do the same thing with our trick before, where we're looping through an array. I could, for example, have A plus 8 times RCX, for example, and I'd be able to copy that into RSI. So for the moment, you can probably get away with not having to use LEA, but you'll see as we proceed, it becomes very much a necessary evil, particularly when we start talking about 2D arrays and things like that. It makes your life much easier to use load effective address. Now, obviously, this move instruction is useful, but it feels like we have a fair bit of machinery here. We have this class of string array instructions, and we have this rep operation that can repeat this simpler instruction. But obviously, we need to have a little bit more diversity than just that move. So there's a couple ones that I'm going to go through that are quite useful for a number of situations. So before I get to the other variants, I just want to specify something. The first instruction we discussed was of the form move string byte. So normal move, an array of elements or a string of elements of size byte. But what happens if you don't have an array of bytes? What if you have an array of words or double data words or quad words? What do? Well, you can actually use the exact same structure. You simply change the last letter to correspond to the size. So this is for a word. This is for a double word or double data word. And this last one is simply for a quad word. The one thing that is slightly different is that in the case of move SB, so this instruction over here, we would increment the address of both the source and the destination by 1. However, if I am using a different size, I will actually increment the address of the source and the destination by the size I'm working with. So say I'm using move SQ, I'm working with quad words, I will actually increment RSI and RDI's locations by 8. So that's simply because to get to the next element in an array of quad words, we would have to increment by 8. Same thing applies if I had a move SW. That would be a situation where I'll increment by 2. If I have move S double data word, I would increment by 4, and obviously quad is 8. So we can perform these operations for bytes, words, and quads. Unfortunately, we don't have the ability using these repeating string instructions to work with more complicated structures like a struct that could, for example, have a size of 17 bytes. We don't have that versatility, but we are able to work with bytes, words, double data words, and quad words. So what were the other instructions that I wanted to get to? Oh, there's one more thing I still need to specify. Up until now, we've relied on the fact that when I call, for example, move SB, I increment the source and the destination address. Now, actually, it's possible for us to increment or decrement. Now, the direction of this movement, so either increasing or decreasing, actually depends on the direction flag. So a direction flag is much like the other flags we've discussed, so like a zero flag, sign flag, carry flag. Direction flag is another flag we have at our disposal. And actually what happens is if the direction flag is set to 0, we increment. And that's the situation by default. So if you start up a program from scratch and nothing else is executed, our direction flag is actually set to 0. If we set our direction flag to be 1, we actually decrement every time we call move SB. So we move in the other direction. So instead of, for example, adding 1 with move SB, we will subtract 1 with move SB from both the source and the destination. So how do we actually set this direction flag? So either to 1 or 0. To set it to 1, we simply use std, so it means set direction flag. If we want to set it to 0, we simply use cld for clear direction flag, and it will do the setting for us. Now, I would actually advise that even if you intend to increment the addresses, I would call cld anyway. And I say that because in a small bit of code, you might know what has happened before. However, if we're in a situation where your code is calling functions or even system calls and doing a lot of complicated things, you might not know what the direction flag is at before you execute your instructions. So it's very much a good practice to actually call cld or clear the directional flag, even if you intend to increment, okay? Because then you know for certain it's going to behave as you would expect. Otherwise, you're kind of relying on the register never being altered in the past, which is obviously a recipe for disaster because a lot of things can happen early in your code. So even though in that example we relied on the direction flag being 0 by default, you should actually set it to 0 to make certain using cld if you want to increment, and std, so to set the direction flag to 1 if you want to decrement. Now there's a couple of other instructions that are going to be useful, these string instructions. So we've discussed move. Another one that is very useful is store. So basically the idea with store is you have some value and you want to set many elements of an array to be equal to that value. So say you had an array and you wanted to make sure that every element was set to 20. You could write a loop that would loop through all the elements to achieve that, or we can actually use the store instruction to do this in conjunction with that rep instruction. So here we have store SB, so STO for store, string instruction, and of size 1 byte. What this does is it will, in the case of store SB, is it will store the byte that is currently in AL because AL corresponds to being 1 byte, at the address specified in RDI. Remember, RDI is often our destination register, so the same thing applies here. And it will increment RDI by 1. Okay. Now, how much it increments RDI by will actually depend on the size specified. So if that B was, say, for example, Q, we would actually increment RDI by 8. Okay, because it will depend on the size. But in the case of store SB, we'll increment RDI just by 1. And the same thing applies with regards to the direction flags. The direction flag will dictate if we increment or decrement RDI. So let's use this as a little example here. So I want to set all elements of this 1 million element array to have the value 1, and let's say that this array is at location, or address rather, destination. Okay, so that's somewhere in my data segment or my BSS segment. So first thing I'm going to do here is I'm going to load 1 into EAX. So this is the value that I'm going to use to store everything. Now, first thing to note here, for this example, we're assuming here that destination is some array of data double words. Okay, that's what we've decided here. Now, in the case of store SB, the value that we would, or the default value that we're going to set all elements to, was stored in AL. However, if we work with a larger size, we use larger versions or larger parts of this register. So in the case of store SD, we actually are going to use the 32-bit register, or 4 bytes, and that in this case obviously corresponds to EAX. So that's why I'm moving 1 into EAX. Then I'm going to move this 1 million into ECX, and this is basically so that I can decrement my counter using repeat. This is what the textbook used. This would actually work perfectly fine if I used RCX. That wouldn't have caused any issue here. Then I'm going to load my destination into RDI. I'm using LEA, so load effective address. I could have used the move variant as well. And then I'm going to simply call rep followed by STOSD. So I'm going to store the value 1 at each of those locations in my 1 million element array. Each time I execute this STOSD, I will end up moving my destination register. In this case, we're incrementing, so I'm going to move it up by 4 bytes because we're working with double data words in this example. Now, there are 2 more useful instructions. There are a couple more, but I think these are the 2 most useful in general situations. The first one is scan, and the second one is compare. They're quite similar to each other. So with scan, what happens is there is some collection of data that we wish to scan to see if it contains a specific value. So I have a big array, so it's 1 million elements, and I want to scan through to check if it contains a specific value. Kind of like we were looking for a character in our null terminated string earlier. And the way in which it works is the value that we're looking for, we put in the corresponding sized version of RAX. So if we're looking using scan SB, we're going to use AL. If we're using scan SW, we'll use AX. Scan XD, we'll use EAX, and if we're using scan XQ, we'll end up having RAX store the value we're looking for. Again, we load the destination register into RDI, the destination location into RDI, and then we simply call scanx using repeat. However, we need to actually use a variant of repeat, which is rep-e, which is similar to repeat in that it will perform the operation. So in this case, it will be scanx. It will shift the RDI register based on the size of the element we're working with. Again, also depending on the direction flag, which way if we go up or down. However, what's different here is that it will not just continue until RCX is 0. It will continue until RCX is 0 or it found the data it was looking for. So if the current element is equal to the one that we've stored in this register, so say we're working with just bytes and the current element is actually equal to what is in AL, it will stop at that point, which means we can actually use the value in RCX to deduce the index of the element we were looking for. So that's really, really quite useful. Compare is quite similar to scan, but instead of taking one fixed value and looking for it in an array, we're basically doing a pairwise comparison across 2 arrays. So you could use this as a quite effective way to check if 2 chunks of memory were 100% identical. So here the operation is CMPS, so compare a string instruction, and again you'd specify the size, so it would be byte, word, double data word, or quad word. And same as before, we load our source and destination registers into RDI and RSI respectively, and we end once RCX has reached 0 or a match is found. Now, in order to make this match is found work, we once again have to use this rep-e. Okay, so we repeat until RCX is either 0 or we actually manage to find what we were looking for. Now, you actually have a choice here with this rep-e on how you want to stop. In this situation it will basically search until it finds equality. However, if you're trying to do exactly what I was referring to try and check if 2 pieces of memory are actually identical, you could use rep-any. So basically you repeat until they're not equal. So if you got to the end and RCX got to 0, you know that the 2 pieces of memory are identical. So it's a very efficient way to do that kind of test. So that brings us to the end of this lecture.